All right, we're going to continue with section 15.6 in this video. We're going to do some examples from the section. So we are on page 1046. We're going to start with number 2, which says in exercises 1 through 4, sketch the boundary of the surface and indicate the induced orientation on the boundary. So remember, in the end of our previous video, we were talking about how a surface induces an orientation on a boundary. So what we're going to do here is we're just supposed to sketch the boundary, but for this first one, it's going to look like I'm basically sketching the surface as well. But if I were sketching the surface, I would actually shade things in. So they give us 3 faces of a cube, and the faces are in the coordinate planes. So we have one face in the YZ plane, one face in the XY plane, and another face in the XZ plane. So a point on the surface, I just specify kind of how this is set up. The origin is one of the points on the surface, and then we'll just label a couple of these other points. So this is 1, 1, 0. This is the point 0, 1, 1. And this right here is the point 1, 0, 1. All right. Then on the surface, they give us some normal vectors. There's the one that comes out of the XY plane and goes directly up. There's one that comes out of the YZ plane and points directly out of the page at us. And then there's one that comes out of the XZ plane and points directly to the right. So if you wanted to, you can sketch a stick figure on this boundary curve wherever you want to, as long as his or her head is pointing in the direction of the normal vector. And if we were to sketch one, say we started on this line segment right here, and we were to sketch a stick figure, and remember the surface needs to remain to the left at all times as that stick figure walks around the boundary curve. So if we were to sketch a stick figure right here, the stick figure would need to walk that way. Now, what happens when the stick figure gets on here? Now, hopefully, any problem you encounter, it does remain the same as you go around. But we'll look at one a little bit later actually in a later section where we kind of want things to switch. So here, if the stick figure were on this line segment, then the head should be pointing out directly at us and still remain the same. That same direction would be the correct direction. And then if the stick figure would get up here, same thing, head should point that direction. Arrows would keep going the same way. So that would be the case all the way around. So that's the induced orientation of the boundary curve from the orientation that was given for the surface. All right, so let's look at another one of those. So look at number 4. And so number 4, the surface that they give us is a cylinder, and it's a cylinder that's closed at the top and the bottom. I'm assuming it's supposed to be closed at the top and the bottom, although they don't, just from the nature by which they shaded it. So but because we're only sketching the boundary curve, we're not supposed to sketch the surface. One, we're not going to have any shading, but we also won't have any sides on our cylinder, because the boundary of a cylinder is just going to be a circular region at the top and the circular region at the bottom. That would be the boundary curve right there. That any vertical line that you were to draw on the side, that's actually part of the surface. It's just the way we have to look at it in 2 dimensions. But imagine it in 3 dimensions. That wouldn't be a line on the side. It would just be what the surface is on the side of there. So now they also give us in that picture the normal vector. it's pointing that way. Now it's coming off the cylinder, of course, but we don't want to sketch the cylinder because that's not part of our boundary curve. So now, if we were on this part of the boundary curve right here and our head is pointing in the direction of that normal vector, which way would we have to walk to make sure that the surface, which is where the normal vector is on the surface, to make sure that that normal vector was in our direction of, to make sure the surface was to our left as we walked, we would end up having to walk to keep the cylinder, the side of the cylinder to our left. We would end up having to walk in this direction. All right, now similarly down here, if we were down here, but we needed to keep, our head is pointing in the direction of the normal vector, but when we walk, we need to keep the side of the cylinder to our left. Then in that scenario, we would need to walk here. So it flips on this, where the boundary curve, this part of the boundary curve goes in one direction and this part of the boundary curve goes in the opposite direction. But this is not a continuous boundary curve as like it was on that one. So sometimes we'll encounter stuff like this, and this will kind of be important to us in the next section, or in the development of a technique that we'll use in the next section in 15.7. All right, so now let's look at actually evaluating a surface integral of a vector field. So we are going to look at number 10. So we're on the same page, number 10. And actually, I'm going to give a little note before we start this. In exercises 10 through 12, use 4 or 6, so equations 4 or 6 in the textbook, to evaluate the surface integral over sigma of f dot n ds. So remember, the textbook uses sigma, whereas I use s for our surface integrals. And they give us two equations they want us to use. One of them is just the basic equation that I've already given you, while the other equation is kind of a shorthand approach, a shortcut approach using our favorite parameterization that we've been talking about for the previous couple of sections. So equation, let's talk about that shorthand approach, or our favorite parameterization, in this section. So before we actually even get into 10, so maybe I should, I'll put it over here. So as usual, there is a condensed formula that can be used for your favorite parameterization. R of x, y equals, where x equals x, y equals y, z equals f of x, y. So that's our favorite parameterization. And that formula in this section is the surface integral over s of f dot n ds. That equals plus or minus, and I'll refer you all in the textbooks as to what page this is on the textbook, because I'm going to write out my notation a little bit differently just because I think it's less cumbersome than the textbook's notation. Plus or minus the double integral over r, where r is determined by your parameters x and y here, of negative m of r of x, y. Then, oh, and actually I need to talk about what m is, so let me specify that as well. I'll do that part at the end. So it's negative m of r of x, y times the partial of f with respect to x. I don't think I have enough space for this here. Minus n of r of x, y times the partial of f with respect to y. Sorry, I'm going to have to go to the next line for this. And plus p of r of x, y. Then, so you're integrating this entire thing right here. With respect to a, where the vector field f of x, y, z is equal to the vector m of x, y, z, comma, n of x, y, z, comma, p of x, y, z. So the textbook doesn't use this notation. They actually write out your parameterization in there. So they just write out x, comma, y, comma, f of x, y in there instead of r of x, y. But another probably even easier notation is we could just also write, or I think I can fit this on one line, surface integral over s of f dot n ds. The double integral over r of negative m times f sub x minus n times f sub y plus p, and the p is basically times 1, and I'm going to write that there and I'll explain why I'm writing it here. dA. So this is where, so usually in the first approach I gave us at the very beginning of the lecture was that we had to do r sub x cross r sub y, and that would be part of our integrand. So we would take our parameterization, plug it into our vector field, and then we would dot that with r sub x cross r sub y. All of that is done for us already in this formula and this formula. These are the same two formulas. It's just a lot easier to write because you don't have all the x's and y's swimming around in there, but you do have to remember that there should be x's and y's swimming around in there when you put your formula together. But really what I want to point out is, because we still need to determine if we're going to use this shortcut formula, we still need to determine should we be using plus or minus, and how are we going to do that if we didn't compute this, if we didn't compute the cross product ourselves. So we're just going to tell you what that cross product is. So this is where r sub x cross r sub y is equal to, and it's just negative f sub x, because this really is a dot product. This is m, comma, n, comma, p dotted with the vector negative f sub x, negative f sub y, comma, 1. So this is what's going to tell us, should we be using a plus or minus? So the nice thing here is that we can see that this vector right here points upward. So if our problem says that this surface has upward orientation, then we know this normal vector that's in this formula already for us has upward orientation, so we leave the plus sign. If the problem says that our surface has downward orientation, this normal vector that's used in this formula has upward orientation, so we need to use the negative in that scenario. So just knowing that the z component here in this formula is 1 for the normal vector, that tells you that the normal vector points upward, and you can make your determination from that. All right, so now that's kind of a lot of information to do this, to start out this problem 10, but it's going to be useful information because, as I've mentioned in previous sections, if you can use your favorite parameterization, go for it, because a lot of times it's going to make your life way easier. All right, so now actually let's do number 10. So number 10 says, so this is, sorry, I said I was going to reference where this is in the textbook. So this is equation 6, I think, that they were talking about in the textbook, and it's on page 1042. So this is, let's put it, I'll just write it down here. Equation 6 on page 1042. And that's not this part down here, it's just this whole thing up here is on that page. All right, so now number 10. And instead of trying to memorize, well, you all won't have to memorize that, but kind of just keeping this approach in mind, that will make things a little bit easier. And you all know just from practice that, okay, I have to take my parameterization and plug it into all of these functions. All the functions, when I say function, I mean m, n, and p, not f sub x and f sub y. All right, so now number 10, they give us the vector field is y negative x 8. So f of x, y, z is y negative x 8. And they tell us sigma, or S for us, which I'll call it, is the part of the paraboloid z equals 9 minus x squared minus y squared above the xy plane. N is directed upward. All right, so the surface for us is z equals 9 minus x squared minus y squared, and they say above the xy plane, which tells us that z is greater than or equal to 0, and they say tell us that n, the normal vector, is upward. All right, so now we get the surface. We know we need to parameterize that surface. First thing I'm going to go for is, can I solve for a variable? Can I solve for x, y, or z? They already solved for z for us here. So my natural instinct is I'm going to go for using my favorite parameterization. There are other parameterizations you could use, of course. You could use cylindrical if you wanted to. I'm going to go for my favorite one because if I use that, everything is already done for me. I don't have to compute any cross products or anything like that. All of that, the entire integral is set up for me. I just have to plug stuff in and that's it. So here we're going to use x equals x, y equals y, and z equals f of xy, which for us that's 9 minus x squared minus y squared. But I'll just write out the f of xy first. 9 minus x squared minus y squared. Now what we can do is, if we're going to use this formula that we have up here, then we just need to plug stuff in here. We need to figure out, should we have a plus sign or a minus sign in front of it, and that's determined by this says upward, and I already said that this is built in as upward, so we're just going to use the plus sign. So that means our integral that we want is the double integral over, the surface integral over s of f dot n ds equals, oops, I forgot about my bounds for my parameterization, so I'm going to do that part in just a second. So what we would do is look at this thing in the xy plane. So setting z equals 0, and we'll get x squared plus y squared equals 9 is what our region is going to be. So we would get that circular region, but for now, I'm just going to put double integral over r of, so now negative, can I get both of these on the page at the same time? There we go. Negative m of x, y, z. So you have to plug your parameterization into this thing. So we're going to get negative. Now m of x, y, z, what is m? This is m right here. So we'll put an m right there. This is N right here, and this is P right there. So we're going to take M, this, and we're going to plug in our parameterization. So everywhere I see an X in here, I'm going to plug in an X. There are no X's in there. Everywhere, because my parameterization says X should stay as X. Everywhere I saw Y in here, I will plug in whatever I see right here, and it's Y, it's just going to stay Y. Everywhere I saw a Z in here, I will plug 9 minus X squared minus Y squared. There are no Z's in there. So this is just negative M, and then times f sub x, the partial of this with respect to x, which is negative 2x. All right, so, and that covers that part of the formula. Minus n, I take n, which is right here, and I substitute my parameterization in there. So whatever, if, say for instance, x had been whatever, cosine of theta, that's what I will plug in right there. But x is not, x is just x, so I'm going to leave that there. There are no y's in here, there are no z's in here. If there were a z in here, somewhere in this n, I will plug in 9 minus x squared minus y squared. There are no z's in there. So I'm just doing plus, because it's minus the negative x, and then times f sub y, which is negative 2y. Then lastly, plus p times 1, and we would take our parameterization and plug it in to whatever we had for p here. So we take x equals x, plug it in there, y equals y, and z equals this, and plug it in. But our p is constant, so it's just 8 times 1. So 8, and then this dA. And so we have 2xy minus 2xy, so those cancel. And then we're just integrating 8 dA. We can take that 8 and pull it out. We have 8 times the double integral over r of 1 dA, which is just 8 times the area of r. And although I should have done it, I didn't specify what our bounds were earlier, but it won't matter here because we're just looking at, again, set z equal to 0, because we're looking for what x and y vary between, and we'll get x squared plus y squared equals 9. So we get a circle of radius 3 centered at the origin. So our area is going to be 8 times pi times the radius squared, and that would be our answer there. All right, so I'll stop this video here, and then we'll continue with section 15.6 in our next video.